And now trees. And now trees. On the syllabus, this is called validity 3 because it's the third and distinctively, substantively new third way of testing an argument for validity or demonstrating the validity of an argument, demonstrating that given a set of premises, if the argument is valid, the conclusion follows. First one, of course, is truth tables, and the second one was the rules of inference that we've just been looking at over the past couple of sessions. We're going to return to the rules of inference next time, kind of an elaboration on that method, an elaboration or an extra detail you can do. But with truth trees, we have reached the third and final approach to validity in propositional logic. In some ways, the truth trees may remind you of the truth tables because they apply a specific test for validity based on the definition of validity. Again, the definition of validity is that there are no instances, no cases, no counterexamples in which all the premises are true and yet the conclusion is false. Okay? The truth tables display on their face the rows in which all the premises are true, and you simply look across the row to see whether the conclusion could be false. In another way, the truth trees, or proof trees as this author calls them, may remind you of the rules of inference approach, the proof approach, in that we start with the premises listed in argument form, we apply certain rules to them, and then we get the result. I want to emphasize these points of continuity because in some respects, the truth tree might look like, well, to be frank, might look like just another headache. Is this just one more set of rules, one more game that we have to learn to play? Why, when we've already learned these two other methods? Indeed, in a way, there's no inference going on here. We're not starting with premises and finding our way through different implications of those premises to arrive at the conclusion. Instead, the trees offer a way, actually more like the truth tables in this respect than you might initially think. The trees offer a way of displaying all the premises and the negation of the conclusion. And then you ask, is there any way that these can all coexist? All the premises and not the conclusion, but the negation of the conclusion. Because if the premises can, and I'm using this word loosely, vaguely, if all the premises as stated can coexist with the negation of the conclusion, then in that old-fashioned sense, the premises don't force, they don't compel the conclusion in the non-negated form to be true. And then the argument is not valid. If, however, we negate the conclusion and then come up to one contradiction after another, that is to say, if you start with those premises, there's no way you can negate the conclusion. Why? Then you've shown that the argument is valid. Now, I happen to be a fan of the truth trees. I was actually forced to learn them. I don't mean in a course that I took. That's just a normal way of being forced. I mean, when I originally agreed to teach logic at my first job, the chair of the department said, here's the book we use. and gave me a book to use that exclusively relied on truth trees. Well, what could I do? It was my first job, and I said, sure, I can. I guess I can do this. Well, I found that they were a flexible, pleasant, reliable way of dealing with arguments, and they became my go-to. If someone, and this does actually happen once in a while in my walk of life, if someone throws a symbolic proof at me and says quickly, can you check this for validity? And no one's watching, I always do it with trees. Okay, I hope to show in this session why that is. Now it's funny, I want to quote from the book here. In the concluding page of Unit 23, in which our author Klink has talked about trees, she says, once you catch on to this method, it is very easy and very fast. Sounds like a reason to put it square in the middle of the textbook, right? Not in an appendix almost, Unit 23. Why then don't we teach it to begin with? Mostly because it is really not the way we reason in ordinary discourse. We generally reason linearly and make use of the standard inference patterns you have learned. Well, I have a lot of respect for this textbook and for its author who has put it together really in a fine way. I really have to differ with that claim. Natural deduction, that is, for example, the rules of inference that you've been learning and the replacement rules that they apply, it's all well and good. It's even pleasant in its way. Only occasionally does it reflect how we reason in ordinary discourse. And indeed, I would say that often enough, the fundamental ideas of the truth trees themselves reflect how we reason in ordinary discourse. Okay, so I don't see the strong argument against truth trees that some people seem to find operative. And on the other side, I can see at least two reasons in favor of the truth trees. Permit me to advertise trees to you now. That might make them your own go-to method when someone throws a little argument, especially an argument in propositional logic, but also an argument in predicate logic, and says quickly, can you see if this is valid? First of all, the truth trees are more straightforward to apply, okay? Once you've got the rules down, and the rules are more commonsensical than you might think, why then with only occasional examples, you can make the tree work. You don't have to develop strategies for your arguments in the way that you often have to do with rules of inference. And second, although this second feature is not always the case, it's not ironclad, but it's often the case. If you recall, when you use the rules of inference, when you're practicing natural deduction, and you arrive at the conclusion, well, then you've shown that the argument is valid, because you could not have, I mean, unless you made a mistake, you could not have reached the conclusion unless the argument were valid. But suppose you don't reach the conclusion. Can you deduce that the argument is invalid? Well, no, you cannot, because you might simply have failed. You might simply have erred. You might simply have not discovered the way to get from the premises to the conclusion. So the inferential method won't necessarily give you an answer as to whether or not the argument is valid. if you fail to reach the conclusion, you may retain as a hypothesis the possibility that the argument is invalid, but you cannot say that you've shown that the argument is invalid. You can only show that an argument is valid. Now with truth trees, again, it's very clear when you've shown that an argument is valid. There's still a lingering possibility that because of some mistake in the order in which you branched out the trees, you come to believe that the argument is invalid when in fact it is valid. But if you practice the trees correctly, and except for some unusual cases, I think you can rely on the answer that the argument is valid when the tree shows it to be valid, invalid when the tree shows it to be invalid. Now, against these advantages of the tree method, we might say there's the problem of the initial learning curve. Okay, all right, well, I can't deny that. There's a learning curve. We're trying, of course, to survey many different ways of talking about validity, demonstrating validity, and teaching symbolic logic and teaching methods of demonstrating validity. And you never know when you might walk into a classroom and have to teach the truth trees. Okay, there's the learning curve. What are these rules in the truth trees? Well, there are rules that you apply, and then there are the rules about how to apply the rules. The rules themselves might look at first like a bunch of additional new commands, new things you have to do. They're essentially things you already know. They're really just replacement rules. So we don't really use rules of inference here. These are really just replacement rules translated into a two-dimensional branching diagram. You're diagramming the replacement rules. So that's the rules themselves. And then the rules about how to use the rules, well, they're pretty simple. There's the one fundamental rule, which is that you negate the conclusion. You negate the conclusion and, as it were, see what follows. And then there are the principles of branching and marking off contradictions. Okay. Just a little patience, and I think you can learn all these rules. And in fact, I think you can learn them without even having to stop and write them out and get to know them the way that you did with the others. The idea is that you begin with the premises and you create, I like this metaphor I just used. You create a diagram. You're trying to see how all the premises can fit together. You can't really work with the premises as they are, okay? So you have to either stack the parts of them or branch them. So, for example, if you have a conjunction of A and B, you stack the A and the B. If you have a disjunction, if you have the disjunction of A or B, you branch them. What if you have a material conditional, A horseshoe B? Well, this really should not be a surprise. As we emphasized in the preceding lesson with replacement rules, but in a way, as we've been talking about all semester long, and what we know of the conditional statement A horseshoe B is equivalent to not A, the negation of A, or B. Well, it follows then, because you're always stacking the ands, you're branching the ors. Stack the ands, branch the ors. A material conditional looks like an if-then. It looks like a new kind of connective, new kind of grammar. In fact, it's the same old one. It's the or, except for the negation. You negate the antecedent. So here you have not A or B. Those are branched. Okay, what else are you going to throw at us? A little bit more complicated is A if and only if B. A little more complicated, but also in that respect, a little more interesting. You both branch and stack. And what do you stack? Well, there are two possibilities with a biconditional. You can think of this going way back to the truth table for the biconditional. The biconditional A if and only if B is true when A and B are both true. It's true when A and B are both false. If A and B have different truth values, it's false, right? So here you're looking at the two ways that the biconditional is true. It's either A and B, or it's the negation of A and the negation of B, all right? Okay, so that's what you do when you're presented with any non-negated connective. What if the connective is negated? Well, we've learned just enough about replacement rules to see how we can translate negated compound statements into the diagrammatic form they take in truth trees, like this. We've got the conjunction A and B. You negate that, but you remember De Morgan's rule that a negated conjunction is the disjunction of the negations. Right? Not A and B is not A or not B. And or, stack the and, you branch the or. That's it. There are really no other fundamental visual demonstrations of on the truth tree besides the branching and the stacking. And likewise, or oppositely, if you prefer, suppose you have a negated disjunction. Well, again, if we had not done the replacement rules, sure, I could understand you saying, well, there's an arbitrariness, there's a surprise, there's a peculiarity. I can't handle all of these rules about truth trees. But in fact, given that we've done the replacement rules, well, you know what we're going to do. We're going to do in this instance the negation of a disjunction, all right, not parentheses A or B, is just the same as not A and not B. So we stack. Now, sometimes you might have to keep it in your head. You might have to maybe go to a piece of scratch paper and write down, oh yeah, this is what this is. And what about the negated material conditional? All right, well, okay, I'll grant you this one we have not seen a whole lot of all the time. Here you just remember that, I guess you'd use two replacement rules together. The A horseshoe B is equivalent to not A or B. And then you negate not A or B, and you get a conjunction of A and not B. But again, it's nothing you haven't seen. It's nothing you don't know. If you simply walked into a room and you're born haven't thought about logic, haven't learned the connectives, and someone says, when this, the negated conditional appears in a proof, you then stack the antecedent over the negated consequent. Well, then, sure, I grant you, that would be a bit of a surprise. But here it really follows from replacement rules. And let me just repeat something that I said at the beginning of this session. It's interesting that in a way we're not doing any inferential reasoning when we use the truth trees. We're simply taking all the premises and the negated conclusion, and we are arranging them to see whether there's going to be any contradiction in that set. Now, one of the things about the biconditional is that maybe you find this a bit of a surprise, maybe not. The conditional became branches and then stack the A and B, not A, not B. When you negate that biconditional, structurally it's the same. You branch and then stack, but here you stack the other two possibilities. One of them negated, not the other one. Okay. What are these after all but visual demonstrations of the replacement rules, of identity rules? That's the rules of the truth trees. And then I said we have the rules for applying the rules, the proof tree method. Let's do a couple of simple ones here, just so you can see what the basic rules of the game are. Let's look at our old friend modus ponens. If A, then B, A, and you want to show that B follows. Okay. So you negate the conclusion, as we're also going to be doing with the indirect proofs next time. We're fundamentally demonstrating validity of an argument by showing a contradiction when the conclusion is negated. It's an age-old approach. I mean, hey, Zeno's paradoxes, in a sense, are indirect proofs for Parmenidean ontology, but let's not get into that. So we've got the premises here, and we've got the negated conclusion. Now we start to branch, but we branch very quickly because we've only got one line, line one, that needs to be subdivided. It's a material conditional. So it branches into not A on one side, B on the other. Well, not A. So we're looking all the way up the tree. And if we see a contradiction anywhere in a path, starting with A, going down here, then we have to block it off. You can say truth can't travel along here because you've got an A and you've also got a not A. What about here? You've got a B, but further up you've got a not B. That becomes impossible too. That's a way of saying we have shown in a visual manner that negating the conclusion leads only to contradiction. There's no way you could have all the premises true and the conclusion false. No way. It's contradictory. That's it. Therefore, this argument is valid. Now, I hope you remember the invalid form that almost mimics modus ponens, that is the fallacy of affirming the consequent. If A, then B, B, therefore A. What happens when we try to demonstrate validity of that argument using the same tree method? We negate the conclusion. We get the negation of A. Negation of A, B, that's from line 1. Well, there's no contradiction so far here. It's not A and a not A. What about over here? Well, there's no contradiction so far. There's a B and a B. Well, we simply bring in all the other lines of the argument, don't we? Yeah, except there are no other lines, right? We did everything we could with line 2, which was nothing. We did everything we could with line 3, which was nothing. We did everything we could with line 1, which was to branch it with a negated antecedent, and we wound up with no contradictions. There's no contradiction here, no contradiction here. We say that those paths are open. And when there is even one open path in a tree, the argument is invalid. Okay, so again, we've shown that the argument is invalid. Not so easily done with rules of inference. Very easily done with truth tables, I grant you, truth tables. But people find truth tables tedious, cumbersome at times. Well, you could object that truth trees take up a lot of space. Our author makes that comment in the book. Well, to demonstrate the complete proof of this would take up a lot of space. But then, that makes me think, back in 1879, okay, all right, I wasn't there, but back in 1879, when Frege wrote the Begriffsschrift, he had a very awkward, space-wasting way of showing validity, of demonstrating a proof. And when he was told that his notation took up a lot of space on the page, he remarked rather tartly, "The printer's convenience is not a summum bonum." Okay, well, so too we might say, yes, you might use up a little more paper this way. Okay, I grant you, that's the big downside of the tree method. Let's just go slowly through a case or two so that it's not so baffling. There's a premise. A horseshoe B or B horseshoe C. And our next premise, not C, horseshoe, not A and B. Just to save space, although it's against the rules, well, it's against the etiquette of the truth tree. But I'll tell you that our desired conclusion is if B, then not A. Okay, if B, then not A. So we negate that conclusion. We say not, if B, then not A, to negate the conclusion. Okay. Now, the order and the textbook is quite good in how it explains this fact. Strictly speaking, the order in which you break down the premises and negated conclusion into their diagrammatic form does not matter. You ought to get the same answer whatever order you break these lines down in. However, if you start with the branches, if you start with the lines that branch and then have a lot of stacks underneath, it's going to become a more complex, a bushier looking tree than if you start by stacking when you can and subsequently branch. You will get the right answer either way. So from line 3, we've got a negated conditional, and we know, what's a conditional? What's a conditional but a disjunction with a slightly twisted antecedent, okay? And what's the negated conditional but a conjunction? So from 3, we get B, right? And then the negation of A, the negation of not A, which is A. That's the negated conditional. Let's check that we did that. Well, where do we go next? If we start with line 1, we can see that we're going to branch, but then we see looking ahead, we're going to branch off the branches. Line 2, well, actually the same is true. 6 of one, half dozen of the other. I'm just going to start with line 2 because it's a little shorter. So line 2, we negate the C, we negate the not C, we get C, and we have not A and B from line 2. And this we have to branch again to not A, not B. Now on the one hand, you've got your mind on the remaining premises. You want to go back, make sure you have branched and stacked everything there is. But on the other hand, you must be alert to any contradictions that arise as you go, any points at which you can mark off the path, okay? When you see a contradiction. Now, do you see a contradiction on the C side? No, haha, how could there be? That's the only C there. But, why? Here you have a not A, you look up and there's an A. You've already closed off that path. Here's a not B, you look up and there was a B. You've closed that path, and really that's all you have to do with that whole side of the tree. So we've got now B, A, and then C, and only from this C will we go back and branch what we found in line 1. So what did we find in line 1? Let me put a discrete border around here. We have just a disjunction, so we have A horseshoe B over here and B horseshoe C on the other side. Okay, no contradictions yet, but that's okay because we know that those are still compound statements. They need to be broken down. What are we going to do? Do we branch or do we stack? Okay, looks like a conditional. Looks like you think it's a completely different connective. Indeed, in fact, it's just a disjunction. We branch. So we have not A or B, and here we have not B or C. Okay. Okay. This closes off, this path closes off What about the B? No, we look up, there's no not B anywhere in the set of premises. What about the C? There's no negation there, no not C. So that was an invalid argument. Let's try one more. We have the premise, if A, then B and C. We have the premise, if not A, then the negation of B and C. We have not A and B, and the conclusion is not C. All right. So we start by negating the conclusion. The negation of not C is, of course, C. Wherever possible, we stack before branching. So line 3, not A and B, lends itself to a stack. All right. Line 1, I would say, is also going to give you fewer branches. So let's go to line 1 to get the negation of A and then B and C. And I'm just combining two steps here. I'm taking this conjunction here that was in the consequent and I'm stacking it. So we have not A, B, C. This looks like a problem because so far all the paths are still open. Let's see what happens when we go to premise 2. We take the negation of the antecedent A, negation B and C. And here 2A, and then not parentheses B and C. Because once you've got a tree going, of course, you have to put any subsequent branches, right? The branches have to go at the bottom of all the open paths. Well, where we see A's, we're fine. We can close off those paths. The consequence of that conditional was a negated conjunction, however, so that tells you you've got a disjunction coming up. Not B, not C, not B, not C, not B. All right, there's a contradiction. Not C, another one. Not B, not C. How satisfying it is to close off all the paths. I know, you can't get over the intuition. Isn't a contradiction a bad thing? Yeah, but if a contradiction is what you come up with by negating the conclusion, that means that you can't negate the conclusion. That means given those premises, you gotta have that conclusion. That means the conclusion follows from the premises. Now, did we explore in this version of a proof, in the proof tree, did we explore what we might call the hidden inferential relations? Did we show how the premises combine to produce the conclusion? No. Did we demonstrate in a logically adequate manner that the conclusion follows from the premises? Absolutely. And as I said, it was all by showing how we could rewrite the premises so that any contradictions in that set of statements, the premises together plus the negated conclusion, would come to light. All the contradictions came to light. The argument is valid, QED. And that ought to show you why I like using truth trees. You don't have to, but I do recommend them.